Anybody have any questions? We got about 3 minutes before class starts. It's only two of you in here, but if you have questions, now is a good time to ask. Got about 1 minute, just in case anybody has any questions. All right. So we've got 8 of you in here, which isn't the whole class, but it's close enough. So we're going to go ahead and get started. Again, I'll ask anybody have any questions before we get cracked up. Cranked up. I don't know why I said cracked up, but anyways. Anyone? All right, so last time we worked on basically kinematics, which is remember, it's the motion and the study of motion without respect to what caused the motion. So for instance, if you knew position as a function of time, you could calculate the velocity as a function of time, and you could calculate from that the acceleration as a function of time. Or alternatively, if you knew the acceleration as a function of time, even if it's a constant, and you knew certain specific initial conditions, then you could actually integrate A of t equals dv dt to find v of t. But again, you need initial conditions like the velocity at t equals 0 is blah, blah, blah. It doesn't necessarily have to be that, but that makes it easiest. It could be the velocity at t equals 3.798 seconds equals blah, blah, blah. That would work too. It's just, like I said, not quite as easy. And then, of course, you could set that v of t equal to dx dt. Again, integrating that, and as long as you had an appropriate initial condition, you could then determine what x as a function of t is. So again, all of that is kinematics, and now we've discovered not only the kinematics of linear motion, but we've now done the kinematics of rotational or circular motion. So now we're going to move on to the dynamics, and to do the dynamics, obviously, we found the equivalent of Newton's second law, which was the summation of forces equals mass times acceleration, which I said various ways. But in the rotational analog, it's the summation of the torques. In other words, the net torque acting on a object, for instance, is equal to I, the moment of inertia, times alpha, which is the angular acceleration. So we need to make some sense of what the moment of inertia is. And I try to do multiple problems deriving the moment of inertia. If you want to calculate the moment of inertia of actual discrete parts, like for instance, I think your book does one on a something that looks like a framing square. So you could break the framing square, which is a rectangle, and then it turns and goes straight back down like this. You could treat it as one rectangle, another rectangle, and a square if you wanted to, or you could treat it as a longer rectangle with a rectangle. And then you assume that each of those rectangles has their mass uniformly distributed. Therefore, their geometric center is their center of mass. And then you just locate each of those 2 or 3 parts and determine what their weight would be based on, the fraction of the surface area or something like that. For instance, if you had a Freeman square that weighed, 4 kilograms, and you could see that, this little leg has 30% of the area, this little square has 2% of the area, and then this other leg has the remaining 68%. Then what you're going to do is assume the little 30% one is going to have 30% of the mass, and it's going to act as if it's at the center of the geometric center of that part. The other one's going to have 2%, the little square, that's going to have 2% of the mass. So you do 2% times 4 kilograms again, and you put its center of mass at the geometric center. And then again, the third part would be the 68%, and multiply 0.68 times 4 kilograms, and then use the geometric center. And that could allow you to calculate the moment of inertia of the Freeman square. So those are very straightforward. I don't think there's much need for me to show you that. The book does good examples. What I want to do is do the integral ones, which tends to be a little bit more difficult for students, even though it's very much like the moments of inertia and the center of mass that you did in calculations in your calculus course. Well, I say in your calculus course, I think that occurred in Calc 2 more so than Calc 1. So if you haven't had Calc 2 yet, then obviously that's a moot point. So let's go ahead and show you an example. So the first thing I want to do is I'm going to consider just a very thin rod. So a thin rod, yes, I'm going to, yeah, I need to share that, don't I? Is that what you're getting ready to say?
Yeah.
Thank you, I appreciate that. Because I definitely would have forgot, but luckily you said it in just a nick of time. All right, so I've got it turning on. And I've written a bunch of stuff down already, and that's good. I wanted y'all to have all this. So I'm going to now, while you are trying to copy that, for instance, these are just some of the facts that we learned last time. I'm just reiterating them. And I actually gave you units of what lambda and sigma and rho are. And I didn't write the word or very well there, so I just wanted to do that. So let me, for instance, consider a thin rod. So I'm going to say a thin rod is like this. Okay. And that seems to span 1, 2, 3, 4, 5, 6, 7, 8, 9 of these. So I'm going to go at 4.5 of these and put my y-axis, and then put my x-axis right here. And now I'm going to say this is y and this is x. And what I'm going to tell you is that this part right here is at positive L over 2. And I'll continue this line here. And I'm going to say that one is at negative L over 2. And we're going to assume we know L. And I'll also say that it's uniformly distributed mass, total mass equals M, and is uniformly distributed. Okay, that went badly because I just wrote my I so small that it got ran over. Okay, so what uniformly distributed means is that I could cut a single cubic centimeter out of this rod and weigh it. And then I could take that mass in kilograms and divide it by the number of cubic centimeters, and I get a number. And then if I took any other part, which could be a cubic centimeter, it could be a cubic millimeter. Obviously, it's not big enough to necessarily be a cubic meter, but the main thing is any size that I wanted to, I could go ahead and take that and then weigh it and then divide it by its volume, and I get the exact same number. In this case, since it's essentially a one-dimensional object, there's no need to go as deep as thinking about the mass per unit volume. I can just do the mass per unit length. So that's what I'm going to use. I'm going to assume we know this. So I'm going to say, we know. And I'm going to say, we know that too. So we know the L, we know the M, and what we want to find is I equals question mark. And what I'm going to do is draw a line to separate it from the notes that I had originally taken, like that. And that went horribly, so I'm going to erase it. And now I'm going to try to lasso this and bring it down closer. So let's see if I can do that. Maybe I can, maybe I can't. There you go. So I'm going to say, let's call this example. Okay. So the formula for the moment of inertia, or excuse me, yeah, for the moment of inertia is this. So here's our solution. I'm going to use I is equal to the integral of r squared dm. I took time, at least in the discrete version, to write exactly what r sub I is. And I wrote where r sub I is the distance between m sub I and the axis of rotation measured perpendicularly to the axis. So I actually need the perpendicular distance from the rotation axis to the differential mass element in the case of r squared dm, r to the m sub I in the case of I equals a summation from I equals 1 to n of m sub I, r sub I. I am going to also tell you that the rotation axis is right there. It's the y-axis. So what I'm going to do is I'm going to imagine a little section right here, and I'm going to call that dm, and I'm going to say that's equal to lambda times d. Now notice I'm on the x-axis, so I don't need to use some arbitrary dl like it says up there. I'm just going to use dx because I'm actually measuring it across the along the x-axis. Not only that, I'm going to say that this dimension right here is dx, and I think you can also see that this dimension from here to here is actual x, and that is perpendicular to the axis. So that's actually what my r will be. Can anybody tell me, given that I told you the total mass is capital M and the total length is capital L, can anybody tell me what you think lambda would be? And it might help you to look at the note that I made above. Yes, Micah, except not X. What do you think I would use instead of X? Close. I actually called the length of the rod L. So it's capital L. So yes, lambda, I'll say therefore lambda is equal to M divided by L. Okay. And that would be the average lambda in any case, but in this case, we told you it was uniformly distributed. So because it's uniformly distributed, the average is exactly the right quantity. So now I'm going to take my integral, and it's going to become the integral of x squared times lambda dx. And the lambda, of course, is m over L. So I'll now have the integral of x squared dx, and I'm going to integrate that from x equals, x equals negative L over 2 to x equals L over 2. Now, you'll notice that this function y equals x squared, which we're integrating, that function is actually symmetric about the y-axis, meaning if you go to x equals 1, then you're going to square that to get y, and you'll get 1. If you go to x equals negative 1, you're going to square that and get 1 as well. So you see that y of x is equal to y of negative x. That means it's symmetric about it. So I could also replace this for ease if I wanted to with 2m over L times the integral from 0 to L over 2 of x squared dx. And that's true for any what we call odd, or excuse me, even function. The odd function is exactly the opposite. If you integrate from a symmetric range, you'll actually get 0. If you do a Taylor series expansion of sine theta and cosine theta, you'll see exactly why they're called even functions and odd functions. All right, so let's continue. I now have the integral of x squared is going to be 1/3 x cubed. So I'm going to get 2m over 3l times x cubed evaluated from 0 to L over 2. That's going to give me 2m over 3l times, now L over 2. You should remember that when you're doing this, you actually should first consider replacing the variable x with parentheses x, close parentheses, and all of that raised to the third power. Because if you don't do it that way, there's a chance that you won't realize a negative, for instance, has to be squared with it. In this case, there wasn't any, but it would have been if I hadn't changed the limits of integration to 0 L over 2. Otherwise, I would have had negative L over 2 to L over 2, and that could have caused a problem. So in this case, I've got this square cubed. That's going to give me L cubed over 8. And of course, this quantity is L cubed over 8. And 8 is 2 times 4. And that 2 can cancel out with that 2. And let's say this 3 can cancel out with this and leave a 2. Okay. So now that I've got all that written down, I can now realize that I'm going to get 1/12, because 3 times 4 is 12, ml squared is equal to I. And I'm going to subscript that cm, because really that is the moment of inertia when it's rotated through about an axis through its center of mass. Okay, that turns out to be an important thing. So as an example for that, let me show you another one where I'm going to do the same rod, but I'm going to rotate it about its end instead of its center of mass. Okay, I'm really having a hard time getting this thing to do what I want it to do today. There you go. Okay, so there's an example. So we've got that now. Now I'm going to do another example. And I got to take it off of that special drawing now because it won't let me write my letters when I do that. So there's my example. So now what I'm going to do is I'm going to take that same little rod and I am going to allow it to rotate about its end. Oops. It's not good. That was even worse. This thing's really trying my last nerve here. And of course it did that. Ah, darn it. Urgh. It's really making me mad. Urgh. I'm sorry I'm being so obsessive about this, but there just comes a time where you got to put your foot down and say, ah. This might not have been the right time to do that, by the way. Okay, there it is. So now I'm going to draw my axis at this end. And I'm going to draw my x-axis at this end. Well, that was just great. That was the worst thing that could possibly happen. Okay, so I'll do it like that. That's good enough. All right, so now we see that this end is in fact at it's such a pain in the butt. This end is at L, the other end is at 0, and the mass is still, of course, the mass is still M. That's my y-axis. That's my x-axis. M is uniformly distributed. Along, I can say it this way, just I'm choosing to do so that you can pretend like we know L as well. So again, what this implies is, let's write our solution. Lambda is equal to M over L again, and I is equal to the integral of R squared dm. And what I'm going to do is take a little differential mass element right here. I'm going to say that's dm is equal to lambda dx again. And I'm going to say erase just a random smudge because that's what this program wants me to do, evidently. And this is out of distance x, which is the perpendicular distance from the axis of rotation. So now I can say that I equals the integral of R squared dm is going to become the integral from 0 to L of x squared times lambda dx, which is going to be M over L, because that's what lambda is, times the integral from 0 to L of x squared dx, which you can see becomes M over L times 1/3, so I'll put that down here, of L cubed. So you can now see that we get the answer is 1/3 ml squared, and that's equal to the moment of inertia about the end. If you look, there's a table in your book, and you'll see that both of these values are exactly the right answer according to that table. That's helpful. Now, there also happens to be something called the parallel axis theorem, and the parallel axis theorem says that the moment of inertia through a parallel axis is equal to the moment of inertia through the center of mass plus m times h squared, where h is the distance between the center of mass and the actual axis of rotation. So now what I'm going to do is, in fact, make this a third example and see that we get exactly the same answer. So what I'm going to do is continue here. What I know is the center of mass, moment of inertia, is 1/12 ml squared. And notice now the center of mass is actually at a distance x equals L over 2. So our rotation axis has moved a distance L over 2 from the center of mass. And in moving from the L over 2, x equals L over 2 to x equals 0, it's moved the distance of L over 2. So I'm going to say plus m times L over 2 squared, which of course is going to become ml squared. Notice both terms have an ml squared in it. And this is going to be 1/12 plus 1/4. Well, 1/4 is the same thing as 3/12, and 1/12 plus 3/12 is 4/12. So that's all 1/3. And we therefore get 1/3 ml squared. And that's a check. Whoa, Nelly. Any questions on that? So we managed to get 3 examples out of that one little rod. Anybody have any questions about how we did that? So I want to tell you it is useful. You should probably take the time to go ahead and commit this fact or these facts right here to memory, because in fact they're going to be used over and over and over again. Oh crap. They're going to be used over and over and over again in the center of mass calculations, in the moment of inertia calculations. And then next semester, when you go into the 242 course, there's going to be something similar to it, where instead of dm, it's going to be dq. And then it's going to still be lambda dx, sigma dA, or rho dv. So it's definitely worthwhile for you to commit it to memory. So go ahead and start doing that, and it'll help you. Anybody have any questions on any of that? All right. So usually that's about all a textbook will give you as an example. For instance, Halliday and Resnick, that was sort of the Bible for this course for a long time. And that's pretty much the only example they gave. Giancoli, Survey, that was the only examples they gave. There was a couple other books that gave some other ones. But usually they reserve them for the end of the chapter, because there's so few problems we can actually do in physics that we can solve analytically like this, where we actually get a nice formula. So what we're going to do here is we're now going to try a slightly more complicated problem. So what problem I'm going to do in this case is I am going to imagine a cylinder like so. And the cylinder is going to have a height h, and it's going to have a radius r. And I'm going to imagine rotating it about the axis of symmetry of this guy, which, as you can tell, would be basically right down the center of the circle that makes the top. So what I'm going to do is I'll draw a coordinate system, let's say right here. That will be my x-axis. That will be my y-axis. Okay. And with that, I can see that this distance from here right along the top should be r. And this distance is going to be h. And I am going to say the cylinder shown has a total mass M distributed uniformly throughout the cylinder. Its radius is R, and its height is H. What is its ICM? Okay. And I really should say a little bit more than that. I said through the center of mass, but to be honest with you, there's a lot of different axes that could be the center of through the center of mass that aren't the one I'm talking about. So I really shouldn't do that. I'm going to say, what is the I when rotated about its symmetry axis? And the symmetry axis, of course, is this one that is basically the y-axis. So everybody understand what we're asking here? So to solve such a problem, it looks like no one has any questions. So to solve such a problem, we're going to again use I is equal to the integral of r squared dm. And like always, when you go to integrate something, your differential thing that you're using, in this case, it's dm. I've got to actually create a dm such that the integrand, which is r squared, does not vary very much over the dm. Because if it did, then I have to figure out some way to compute a representative r for that shape. So for instance, if I just took, let's say, a big circular disc whose radius is big R, if I tried to use that as my differential mass element, then the R, notice would run from R equals 0 all the way to R equal big R. That's a macroscopic quantity. And I would have to do some kind of procedure to figure out what's the moment of inertia of that particular disk and then add all that up. I don't want to get into that. So what you do is you try to make a differential mass element that, since the integrand is r squared dm, that doesn't allow R to vary by more than a differentiable amount, or more than a differential amount, so by an infinitesimal amount. So it turns out what we can do is, I'm going to do it in green, okay? What I'm going to try to do is create a differential mass element whose distance from the y-axis is it actually will have a front end that is macroscopic, and then it'll have a second end that's only a microscopic distance away. So I'm going to try to do this using the drawing function that it has on here, and hopefully I can do it without it pooping the bed. Now that was horrible, and I don't like it at all, but I think I might be able to use it, so I probably will. Okay, no, I'm definitely not using that sucker. Get rid of you. Okay, now what I'm going to try again is like that. And now what I'm going to try again is like that. Okay, so now you can see the inner radius of that part would be, say, r, lowercase r, and then the radius to the outer bit would be r plus dr. So in that case, the R, which is the integrand, varies by no more than a dr amount, which is infinitesimal. And now I'm also going to draw straight down from that this outer edge, and then straight down from that. Actually, darn it, why did it stop drawing my neat drawing? Okay, straight down from that, I'm going to draw this. Straight down from that, I'm going to draw this. And now I'm going to take this and say, something like that. And I hate that, so I'm not going to do it at all. And of course, it did it again. Okay. So now I can pull this just a little bit to get it out there. Okay, it's probably close enough. And now I'll do one more for the inner circle. And that, of course, should be connected with this guy through a dotted line, which I'm now going to erase because it turns out that I can't do that very well. All right. Anybody have any questions about what the shape is? So it's basically like the skin of a aluminum can. Okay. So this little segment right here, that little dimension is dr. And in fact, if you looked at the area on top, you would say that the area on top sort of would be a rectangle, meaning the inner, well, actually, let's draw this so you can understand. This is going to be R right there, and then that's R plus dr. So if you look, the inner circumference is 2 pi r, and then the thickness is dr. So it's sort of like a rectangular top, in which case the area of the top would be 2 pi r dr. But in reality, what we see is that, oops, I'm doing the wrong color. In reality, what we see is that, and that, meaning the thickness is, well, actually, let me draw this in 3 dimensions, so it might be a little nicer this way. If I draw it in 3 dimensions, I could say, like this, I would say that thickness is dr, but I'd also say that this is 2 pi r is the distance from, oops, is the distance from here to here. But if you look out here, the distance is 2 pi times r plus dr is the distance out here. So it's not really a rectangle. It's actually a rectangle with 2 little triangular pieces on the end. And now if we went ahead and represented it completely, we would see that the height of the sucker is in fact h. So from here to here is h, and we'd see that the differential volume element dv is approximately equal to 2 pi r h times dr. So basically what we're imagining is that this little extra bit, that little triangle on each end, which we might draw like this and this to separate it out. If you cut that little triangle off, then, which is sort of a triangle, but as you can tell, it's actually a triangle, a triangular prism, because it's going to go all the way down on this side and all the way down on this side. And if you cut those off, it would leave a perfectly rectangular shape, the width of which is 2 pi r, the thickness of which is dr, and the height of which is h. So you get 2 pi r times h times dr. Now, I will tell you that cutting out those triangles matter, but it turns out that they only matter to terms of order of dr squared or more. So for that reason, we're perfectly justified by doing this. So that little shell right there is going to be dm is equal to rho dv. So I can now say I is equal to the integral of r squared, and now my dm is going to be rho times 2 pi r, 2 pi r h times dr. So can anybody tell me what rho would be?
Density?
It would be the density, but can you give me a formula in terms of m, big R, and big H?
Pi r squared h over m.
Exactly. Well, the other way around, but yes, rho will be m over pi r squared h. So yeah, you were saying it right. You just had it upside down, but that's exactly it. And that's because it's uniformly distributed. And actually, that would be the average density period, even if it wasn't uniformly distributed. But since they told us it's uniformly distributed, any ratio of mass to volume of any chunk of it that you pulled out would all give you that same answer. So what I'm going to do is I'm going to write the rho out in front. I'm going to say 2 pi h rho, and I'm just going to leave it as rho for right now, unlike what I did before. What I have left is r squared times r times dr. So I'm going to integrate r cubed dr from r equals 0 to big R. That's going to give me 2 pi h rho over 4 times r to the 4th. Now I can plug in all my stuff, specifically my rho. I'm going to have, notice the 2 already cancels out with the 4 downstairs. So I'm going to say pi h over 2, because the 2 canceled out with the 4 in the bottom, unless you left the 2 in the bottom. Now I'm going to write the rho, which is m over pi r squared h. And now I'm going to write the r to the 4th. What we can see here is this pi is going to cancel out with this pi. This h is going to cancel out with this h. And let's do another color line. I'm going to say this r squared is going to cancel out with that 4 and make it a 2. So all I have left is 1/2 mr squared, and that's actually exactly the right answer. It equals 1/2 mr squared. And that's the moment of inertia. Any questions on that one? And yes, you can actually use the parallel axis theorem here. For instance, if you wanted to rotate it about an axis at, notice how I've got it drawn in the x and the xy coordinate system right now. If you took the line x equals big R and you rotated about that, then you could actually use the parallel axis theorem to calculate the moment of inertia about that new axis, because this axis is still parallel to the original axis, which is the y-axis. So let's do that real quick, even though I hadn't planned on it. So this was example, I think this was example 4. Now I'm going to say, I'm going to say, stop using that cool tool that makes your drawings look better. Let's see. What would I be if the axis was x equals r and z equals 0. In other words, I just want to let everybody realize that, hey, I'm keeping this completely in the xy plane. That's why I said z equals 0. So according to the parallel axis theorem, I about a parallel axis is equal to I about the center of mass plus mh squared. So this is going to be 1/2 mr squared plus m, but now I'm moving the axis, which was the y-axis. I'm moving it to the right until x is actual capital R. So the distance I moved it is a capital R. So I'm going to put an R squared here for the h squared. And that gives me 1/2 mr squared plus 2/2 mr squared, which is 3/2 mr squared. So that turns out to be the moment of inertia about the parallel axis. Any questions on that? Okay, that's it. Nothing more? Okay. Let me double check. I thought there was something else I wanted to do. I want to check my notes real quick just to see. I thought there was one more thing I wanted to cover before I jumped into the dynamics portion, but let me check here. Oh, yes, there is a little issue of torque. So when we spoke last time, I had gotten you started on torque, but I hadn't really done everything. So let me jump to that. So we were talking specifically about our experiences with bikes, for instance. So if you imagine that this is the spindle of your bike, then you would have, for instance, there would roughly be the axle, and you could have a crank that was like this, and then your pedal, of course, would come out like this, something along those lines, and it would be a shaft right through there. Now, our ability to ride really fast would depend on how much torque we can give this. In other words, torque is the rotational analog to force, specifically meaning it's the actual thing that makes things rotate. And the bigger the torque is, the more rotational acceleration you can get. In other words, you're increasing alpha by increasing the torque. So, for instance, if you had to all of a sudden get away from a dog or away from someone who's trying to steal your bike or something like that, then you'd obviously want to know how best to accelerate. And probably your life experiences have already told you that when you're going to take off, you're going to have to put your weight over top of the pedals. And when you do that, you'll find that you get the right answer. Okay. So yeah, in other words, you will get the actual torque to be a maximum when your body is over the pedal. And the reason that is because your your entire mass can act on it. And because your entire mass acts on it, the weight would be your mass times g, gravitational acceleration. So that would help. But here's the other thing. If you were actually leaning somewhat, say leaning backwards, then your force might be like that, as opposed to when you stand directly above it, there would be an angle theta. Well, what I'll also tell you is there exists a vector we call the lever arm, and the lever arm vector points from the axis of rotation to the point of application of the force. So if you were to, for instance, put these two tail to tail, they would actually get you a angle theta. And what we find is as that theta gets closer and closer to 0, then we get a much better angle. That's not necessarily the best angle to do. In fact, let me regroup on that a little bit. Let's redraw this so I can make a little bit better sense of it. What we normally do when I told you when we use these formulas with sines and cosines built into them, what we're normally doing is finding the angle that they make with each other when they're tail to tail. So you can imagine actually taking this force vector and moving it such that the tail to tail component, or such that it will be tail to tail. That's probably the easiest way to say it. So if I put this force like that, and that's supposed to be the same force I drew before, it might not be, but I was eyeing it, so I did as well as I can. Now that you see their tail to tail, then this angle right here, theta, is the important angle. And in fact, if that angle is 90 degrees, then we'll get the maximum force out of it. Not only that, if you've ever ridden a bike for like a small kid, you'll notice that crankshaft, that thing coming from the spindle out to connect the pedal to it, those are really short and they're very hard to ride such a bike, especially being a big person like myself, for instance. So what you found, hopefully, from your own life experiences, oh, this is weird. Okay, from your own life experiences, I hope you found that this quantity torque is directly proportional to the length of R of the lever arm. So let me get back to black so I can draw this vector as R. Okay, it's directly proportional to R, and I think you'd also find it's directly proportional to F. But we also would like some kind of function of theta that would be 1 when theta equals 90 degrees. Do y'all know of a trig function that's 1 when theta is 90 degrees? The trig function of 90 degrees equals 1. Yes, very good, Micah. So we'd also find that the torque is proportional to sine theta. And in fact, what that gives us is a way of calculating torque called a cross product R cross F. How do we calculate such a beast? Well, that's what I'm going to show you now. There's several different ways, but let's start off from this argument. By the way, we can also say, let me back up before I jump into that, the magnitude of the torque, which can also just be written as torque without the vector symbol, that's actually going to be R times F times the sine of theta, which notice is exactly the formula we had up above. So that's why that worked out. Another thing that's kind of nice about it is, in general, if you say the vector C is equal to A cross B, then what happens with that is it turns out you can have a vector A like this and a vector B like this, and those two vectors define basically a parallelogram by making a vector parallel to A, speaking of which I need an arrow on that, and then making another vector parallel to B, and that completes a parallelogram. And the area of this parallelogram is equal to A times B times the sine of theta, where this quantity right here is theta. And lo and behold, guess what? The vector C is perpendicular to the vector B, and it's also perpendicular to the vector A. Okay, so that's a general rule about cross products. And also it should show you to some extent that cross products can be used for finding components of vectors that are perpendicular to one another, as opposed to like we did with the dot product, which was for finding components of vectors that were parallel to one another. So now with that, let me show you how to calculate an actual cross product. So we're going to say A cross B. One way of writing that is it's the determinant of a matrix. Okay, that matrix will have its first row being I hat, J hat, and K hat. Its second row will be the first vector. So you have AX, AY, AZ. And your second vector would be the third row. So you'd write BX, BY, and BZ. Now, there's a lot of neat little ways you can do this. For instance, one way you could do it is if I wrote like this, I could say, for instance, I hat AX, BX, J hat, AY, BY, K hat, AZ, BZ. Now I'm going to write another one, the first row again, I hat AX, BX, and then I write the second row again, J hat AY, BY. Why did I do that? Well, it turns out when you do that, you can just take and multiply these three guys, get a result, and add that to the addition of these three guys. Take that and add it to the addition of these three guys, like that. And then what you're going to do is say these three guys, and all this is going to be subtracted, by the way. So I'll say minus this one, and then these three guys, which gives me this answer, and I'm going to subtract that, and then these three guys gives me this answer, and that would be the whole thing. So I add up the three products that come from the three blue arrows, and then I subtract from it the product from the first red, and then I subtract from that the product from the second red, and then I subtract from that the product from the third red. Notice that the key to that is you're never using an item from the same row or the same column twice in a multiplication. So for instance, we had I hat, AY, and BZ. Each of those are in different rows and different columns. And that's the way with all those multiplications. So it turns out another way you can do this is we can write the I hat. Well, actually, I should stick to the blue. We can write the I hat, which is that top left corner. That is the first row, first column. So it has a IJ number of 1 plus 1 is 2. And technically, when you do it this way, you're supposed to, since you're expanding upon that I, you're supposed to raise -1 in parentheses to the power of I plus J. I and J are both 1 here. So 1 plus 1 is 2. -1 in parentheses raised to the 2 power is +1. So I don't have to do anything else. But to make sure I don't repeat the same row or the same column, now I act like column 1, which is I hat AX BX, I act like that's not there. And row 1, which is I hat J hat K hat, I act like it's not there either. And then I'm left with that little 2x2 matrix in the bottom right corner. And the way I do that is I do AY. So I go from, for instance, I go from top left to bottom right. So AYBZ minus AZBY. So that's the way you normally do a 2x2 matrix, is you go from top left to bottom right minus top right to bottom left. Now, the next one I'm going to expand about is J, but J has the problem that it's the first row and second column. So 1 plus 2 is 3. Parenthesis -1, close parenthesis 3 to 3 power gives you a -1. So the way I account for that is I take the remaining 2x2 matrix and I do it in the opposite order. So instead of going top left to bottom right minus top right to bottom left, I do it the opposite way around. So that's what I'm going to do here. notice when I take J, that means the middle column and the top row disappears. So all I've got is the AXBY and the AZB X or AZBZ. So I'm going to go from top right to bottom left first, which would be AZBX minus AXBZ. And now I do K hat, but this time it's the first row in the third column. 1 plus 3 is 4. -1 in parentheses raised to the 4 power is +1. So I can just do my normal matrix for a 2 by 2 matrix. I can do the normal determinant, which is top left to bottom right. So this one's going to be AXBY minus AYBX. So that's another way you can do it in addition to that way that I showed you a second ago. So that's some of the ways you can actually calculate torque. There's other ways as well. Let me put them here. So we've got this so far. But I'll also tell you that you can calculate the magnitude of the torque as R perpendicular to F, R as F perpendicular to R, meaning if I find the component of R perpendicular to F, then I'm doing R perp times F. If I want to do that second version, F perp times R, I take the component of F perpendicular to R. So let me show you an example in which we can use that. So let's imagine for a second that I'm going to do calculate the torque on a Greek letter. So this will be example. This one was example. Let me number this right. This is example 5. This is going to be example 6. Okay. All right. So let's imagine right now that we have this Greek letter here. And actually, I'm not liking the drawing already. So I'm going to draw this Greek letter here. And the Greek letter is going to look like this. Okay. And let's say I didn't really draw this quite as well as I would have liked to. So I'm going to clean that up a bit just to make it a little bit more symmetric and usable. So all those are supposed to be 90-degree angles, even if they're not. I'm going to imagine, for instance, that this thing could rotate around that. So I'm treating that like the pivot point. Or the axis of rotation would go right through that and be perpendicular, all sorts of stuff like that. What I'm going to say is that this dimension is 7.0 meters. I will say that this dimension is 6.5 meters. So you can see that this one goes to there, this one goes to there. Both of these go to the bottom. I will also say that this dimension right here is 0.5 meters. I'm also going to say that this dimension from here to here is going to be, let's say, 4.0 meters. And let's say this dimension right here is 0.5 meters. And I think we can pretty much figure out everything from that standpoint. All right. So now let's imagine that I have a force acting right here. F1 equals 10.0 newtons. Let's say I also have another force. Let's say in this case, I'm going to draw it green. Oops, I guess I'm not going to draw it green. I'm going to say this force is F2 is equal to 20.0 newtons. And well, that's probably pretty good for a start. Okay. So what we can see right here is there's various forms for us to calculate our torque. So the solution we're going to do here is torque is equal to R cross F, but torque is also equal to R perpendicular times F, and torque is also equal to F perpendicular times R. So the R vector is supposed to go from the pivot point to the point of application of the force. So if I take this blue line and draw a vector from here to here, then that is actually R1. In other words, that's the lever arm vector for F1. Similarly, I can see that the lever arm vector for F2 would be this guy. So that's R2. Okay, both of those are kind of crappy, right? Like nothing very helpful to do there, but we can in principle calculate it. So for instance, I could say that R1, has an X component equal to 4.0 meters I hat, and it has a Y component that is 7.0 meters J hat. And then I could say F1 is actually equal to 10.0 newtons, and that points in the negative I hat direction. In other words, I'm treating the pivot point as the origin of the coordinates, and I'm treating this as my x-axis, and that is my y-axis. Okay, so I can go ahead and do the calculation with the cross product, and the way I do that is torque 1 is equal to the determinant of that ugly beast I hat, J hat, K hat, and then of course I'm going to say 4, 7, 0, and then I'm going to say 10 with a negative sign, 0, 0. And for this, I'm going to say I hat times 7 times 0 minus 0 times 0 plus J hat. Now J hat, I'm covering up the middle row and the top column, or excuse me, the middle column and the top row. And I'm going to do 0 times negative 10 minus 4 times 0. And then finally, I'm going to have a K hat. This time I cover up the top row and the right column, and that gives me 4 times 0 minus negative, or excuse me, let's say minus 7 times negative 10. So ultimately, my answer is just going to be 70 K hat. That's 70.0 Newton meters K hat. And that's actually the torque. That's not necessarily the funnest way to do it, but it's a way that'll do it. Now, check this out. If I take the torque 1 and recall that it is the component of R perpendicular to F, then I can just look at this and I'll say, well, F is pointing horizontally, despite the drawing not being perfect, but F is pointing horizontally. So the perpendicular component of R would be the vertical component. Well, I can tell already that the vertical component is 7 meters. So I'm going to do 7.0 meters times 10.0 newtons. And that's going to give me 70.0 Newton meters. Of course, you can still use your right hand rule to figure out exactly what direction it is, but I already got the answer. So it definitely works, and that's definitely a lot easier. If I had, for instance, oh yeah, here's a good way. Let's say I'm going to do a really easy one here. Let's say the force right here is F3 equals 30 newtons. Okay. Now, all I got to do is take the component of R. Let me see. Do I want that? No, I don't want that. Let's take all that away. I don't like that. Ah, here's another one. I'm going to use a nice gray vector now. Okay. Let's say I do this. No, I don't want to do that either. Dang it. No, I don't want to do that. No, I don't want to do that. Oh, well, I'll leave it be. I'll try to think of another example, but I was actually trying to show you one where it's F perpendicular to R, which actually doesn't come up as often, but it does occasionally come up, so it will help you. But I think I've done enough for showing you examples of torques. So let me go on to the dynamics portion, which now I'm going to actually consider a Atwood machine. And this Atwood machine is going to be different from the other one specifically because I can now consider a pulley that has mass and even friction. So let me start off by drawing the situation. So this pulley has a mass M uniformly distributed. And a radius R. So I'm actually saying that so you know, oh, we're supposed to pretend we know that. Okay. Now I'm also going to have a rope going down this way, and there will be a mass hanging from it, and that mass will be called M2. And then there will be a rope over here, and it will have a mass on it as well. And this mass I'm going to call M1. Okay. Now, if I wanted to, I could also add a friction, and I could say maybe the friction force is acting at a radius R, or I could just say the friction torque and just add that in as something, but that's not really my concern. What I want to know is what is A, alpha, torque, tension in the left string, and tension in the right string. Okay, so that's what I really want to find out. Here's my solution. What we're going to use is the summation of the torques is equal to I times alpha. And the way I've drawn this, it makes it look like we're expecting M2 to go down and M1 to go up. So I'm going to consider M2 going down to be a positive direction. So in doing that, what that means is my free body diagram is going to have some very specific coordinates. So the first thing I'm going to do is I draw my free body diagram for my actual pulley. So here's the free body diagram for the pulley. What I have acting on it, of course, will be a force that's in the positive direction. That one's going to be T right. And then there's going to be a force causing a torque in the negative direction. And that one's going to be T left. And we should recognize that this distance right here is R, and this distance right here is also R, and that these torques are actually perpendicular to the lever arms. So I can get that R times TR minus R times TL is equal to I times alpha, and that's going to be equation 1. I'm also going to say the pulley is cylindrical. So I also know that I is equal to 1/2 mr squared. So I can plug that in later and I'll still call that equation 1. Now I've got a free body diagram for mass M2. And mass M2, if it goes down, I'm going to consider that to be the positive direction. So this force right here is M2G. And then this force up here is T right. So with this one, I am going to get M2G minus TR is equal to M2A. And I'm not going to subscript the A because if the mass on the right moves down 1 inch, the mass on the left is going to move up 1 inch. And the pulley is going to rotate such that its circumference moves 1 inch. If that happens in 1 second, then it's going to happen in 1 second for all 3 of them. Therefore, we know their velocities are the same. If it once happens in 1 second and then 2 seconds later it happens in half a second, the same thing's going to happen with all 3. So I know that the accelerations are all the same. So that's the arguments that I'm using here. Now I'm going to do another free body diagram. And this one's going to be for M1. Only M1, when it goes up, that's the positive direction. And that's my TL. And when it goes down, that would be the negative direction, which is M1G. So my equation for this one is TL minus M1G is equal to M1A. And this will be equation 3. Notice my unknowns are TL, TR, alpha, and A. That's 4 unknowns. But because I was wise in making sure all these signs match, so a positive alpha corresponds to a positive A, corresponds to a positive TR, corresponds to a M2 going down, which is positive, all that stuff, then I have the very simple expression A is equal to R times alpha, which is true as long as there's no slipping. So I'll just say no slipping. Okay. So now I can go about this. I'm going to take equation 1 and equation 2 and equation 3. And what I am going to do is take equation 3 minus equation 2. So equation 3 minus 2 gives me the following. What I'm going to have is equation 3, which is TL minus M1G is equal to M1A minus Now equation 2 is, I'm distributing this. This is M2G, which was positive, plus GR, which was negative. I don't think I want to do that. Nope, I don't want to do that. So let's scratch my plan with regards to what I was saying I was doing. Why won't this give me my eraser? It erases every darn time except when I want it. I am going to instead I really wanted to get TR minus TL. Okay, let's solve. What I'm going to do is solve I'll solve 2 for TR, and so I'm going to solve 2 for TR, or excuse me, 2 for TR. Whoa, Nelly. And doing so will give me TR, and this will be called equation 2 prime. It'll give me TR is equal to M2 times G minus A. Now I'm going to solve equation 3 for TL. And this one's going to give me TL is equal to M1 times A, times A minus G. And this is going to be called equation 3 prime. Okay. Now I'm going to plug 2 prime and 3 prime into 1. When I do that, I'm going to start off by dividing both sides by R. So I have TR minus TL is equal to 1/2 MR squared. That's where I substituted the I times the alpha. And then I'm going to divide all this by R. So this one's actually equation 1. So now what I'll do is I'll take that TR, which we found was M2 G minus A, minus TL, which I found was M1 times A minus G. That's going to be equal to MR alpha over 2. So I now see that I have an A in there, and in fact, this quantity right here is R times alpha, which is A. So that's equation 4 that we're using there. So now I can write this as M2G minus M2A minus M1A plus M1G is equal to 1/2 M times A. So I can pull all of the A's over to this side. And what I'm going to get is M2 minus, M2 plus M1. Sorry about that. So M2 plus M1 times G, that takes care of that guy and that guy, is equal to 1/2 M plus M2 plus M1, all of that times A. So I get A is equal to M2 plus M1. I really expected that to come out to be a minus. Did I drop a sign somewhere? I'm pretty sure I dropped a sign. I had to have dropped a sign. M2G minus M2A minus M1A plus M1G. Looks like it worked out. over M1 plus M2 plus 1/2 M, all that times G. That definitely shouldn't give. Yeah, that definitely should get an M2 minus M1. Anyways, this is where we're going with this. Once we have A, then we can plug it back into 2 or T prime, or we can plug it into 3 or 3 prime. That'll let us get TL and TR and so on and so forth. Our time has run out though, so I'm going to let you guys go. We will finish this up next time. Anybody that wants to finish this up in the meantime, you could actually do it for extra credit. And if you remind me, I'll put a place to turn it in. But I'm just going to remind you, watch the M2 plus M1, because I think it's because I think you are free to go, by the way. It should be M2 minus M1. Okay. I'll wait for the last person to leave in case anybody has any questions, but you guys are free to go.
Hey, Professor Younger.
Yes.
Yeah, I sent you a message. I think you messed up the TL. It's supposed to be TL is equal to M1 A plus G. I think.
That would definitely do it. Thank you.
Yeah.
TL is supposed to be M1 A plus G. And yes, you're exactly right. And that would actually fix the minus. Thank you for that.
Mhm. Yeah.
Yep, that's awesome. Thank you, sir. I'm going to
Yeah.
put it in red here.
Yeah.
Who is that? Who is this that's talking to me anyways?
Oh, Micah.
Thank you.
Yeah.
Micah found. And of course, I want to write Micah in completely the wrong way. I put your H before your A. Micah found. Okay, thank you. I appreciate that. That'll actually fix everything, because now it's going to have the M2 minus M1 as I expected. But everything else was exactly right. So that helps me a lot. Anybody else have anything?
Also, I was wondering, so next semester I'm taking you for Uni Physics 2,
Uh-huh.
and I was wondering if I could switch my lab time to another one.
Yeah,
Okay.
I think we might have some problems doing that officially on the books, just because we sort of have a limit that we put out, but
Yeah.
there's almost always someone that drops. So I won't have a problem with it. You can stay enrolled in that other class, and once the semester starts, I'll just let you attend the other one if you want. It won't be a
Okay.
big
Yeah.
deal, as long as I don't have too many people, which I can't imagine I will. So just keep that in mind. I can't. There's never been a time where I haven't been able to do it, so I don't think it's
Yeah.
going to be a case now.
It's
But
just that there's a time constraint because that lab it's at 7 to 10 p.m. and the other one with you, I think that's in the morning
yes.
sometime. Yeah. Okay. So that'll be better.
Yeah, that's not a problem. Like I said, I don't mind doing it. And actually, we normally get a little bit less enrollment in the morning one just because it's a morning one, but sometimes it's
Yeah.
so, yeah, I shouldn't do that. If it is it interfering with another class you're gonna have?
Yeah. It's just like the time,
The reason why I
timing
was
for it.
asking is because you have to do it on the books if it interferes with another time, because otherwise it'll show in the books this one student's in 2 classes at the same
Oh
time.
yeah, I got you. Yeah.
Yeah. So yeah, and yeah, absolutely, I'll do that for you. I've got another person that I haven't met yet that's trying to do the same thing with my 241 class, but yeah, I'll do that for you.
Yeah. All right. Thanks, Professor. All right, I'll see
All
you
right, have
later.
a good one, Michael.
Hello,
Any,
Professor.
yes.
Hi. I had emailed you earlier. I'm not sure if you saw it yet, but I had difficulty getting on the internet last night trying to take the exam, and I wasn't able to even like get into it because my internet just wasn't working last night.
Yeah, is it Angelica? Or
Alyssa.
listen, that's I knew it was an A name. Yeah, that's
Okay.
yeah, that shouldn't be a problem. Let me go ahead and take care of that now. What I'm going to do is I'll open it back up for you, and I'll give you to it. Can you get it done tonight?
Yes.
Okay.
My internet is working. I made sure of it. I was on the phone with them today.
No problem. Yeah, I'll go ahead and fix that for you. And yeah, just get it done by midnight tonight. Shouldn't be a problem. And I'll go ahead and open it
All
for you.
right.
All
All
right.
right. Thank you very
Have a
much.
good one. Good luck. Make a good grade.
Thank you.